So a series is just when we add up the numbers in a sequence. So if a sequence was U1, U2, U3, UN like this, then the corresponding series would be U1 plus U2 plus U3 plus U4, and so on up to some UN. And perhaps the notation we'd used at least to start with, we'd call it the S of n, the sum of n terms. And we can get some quite interesting mathematics and some quite interesting results from this. One thing to just bear in mind, which might come in very handy later on, is if I had S4, well, absolutely that would be U1 plus U2 plus U3 plus U4. But it's also going to be S3 plus U4, the sum of the previous three terms plus that fourth term. That result's quite interesting and might be useful in another video. Now, with these series, we will often need new notation. And what if they're very, very big? We don't want to write down every single term. So we use sigma notation to help us. So again, consider the sum of n terms of a sequence, so a series. We'll use this notation. So this is a capital Greek sigma, and it means summation, the sum of some things. But what things? Well, U's, of course, right? Whatever they are. And we're going to use a new symbol, K, and we'll say that K starts at 1 and goes up. So this bottom part here underneath the sigma sign defines where K begins, right? The start point. And this just means we start by saying K is 1 and we add to it, well, K is 2, and then K is 3, and then K is 4. So we're doing this. We're adding up these numbers. But we need a stopping point. It'll just go on forever otherwise. So we're going to stop when K is N. So we'll pop that at the top. This top part is our kind of like finish. So let's consider this sequence, 1, 4, 9, 16, 25. And we're going to write an expression for the sum. So we're going to have this sum of this, I guess, series now. Well, that sum then, if you take a look, each term is a square number, right? When n is 1, it's 1 squared. When n is 2, it's 2 squared. So if we're going to sum these, and we're thinking about this in terms of k, well, we'll have each k squared added up between 1 and, of course, the last number is going to be n. So that is going to be our expression for Sn. To find each sum, well, we can do this kind of manually, I guess. The sum of the first term is just U1, isn't it, right? So that is going to be 1. S2 is 1 plus 4, right? It's going to be 5. S3 will be 1 plus 4 plus 9, right? So that original 5 plus the 9 for U3, well, that's going to be 14. S4, with the sum of the first 3, we've already got that, plus the fourth term, 16. So this is going to be 30. And then we've got S5 as well. Well, that'll be the original 4 terms that preceded it, plus the fifth term. This is going to be 55. There we go. Okay, so a nice simple question to get us understanding that series notation. Let's take a look at another example. So we'll work it the other way around now. We've given the series in that sigma notation. Let's work out then what the numbers are and evaluate what that sum is. So here in part A, we're going to generate the sequence by just imagining k is 1, and then k is 2, and then 3, and so on up to 7. So when k is 1, we're going to have 2. When k is 2, we're going to have 3, and so on, and so on, and so on. The last term, when k is 7, is going to give us an 8. And then we're just going to add these up. Now, we can, I'm sure you can add this up yourself, but do you know what? We'll do it in pairs. If we take a look at that, we've got pairs there that add up to 10. So we've got 3 lots of 10 plus 5. We have a sum here of 35. Part B. Okay, well, let's just go a little bit slower on this one. We shall start by putting in k as 1 into this. So we'll have 1 over 2 to the 1 plus 1 over, well, when k is 2, we've got 2 squared, and so on. And it tells us that we need to stop when k is 5. There we are. So, writing this out, we'll have a half plus a quarter plus an eighth plus a 16th plus 1 over 32 at the end there. Okay, we've got to add those up. I can assume this is a non-calculated question. Let's write this all with a denominator of 32. This is going to be 16 over 32 plus 8 over 32, 4 over 32, 2 over 32, and then 1 over 32. And if we add up 16 and 8, 4, 2, and 1, we're going to get 31. So we have got a sum that is 31 over 32. So to get any further with our work on series, we're going to need to have some general results understood. So let's start by thinking about two sequences. Let's say we have the sum of some a's, right, where k goes from 1 to n. So what I'm talking about here really is that is a1 plus a2 plus and so on, all the way up to an. And let's think about another one. Well, this will be very, very similar, but with some b's. And I'm just using this notation to kind of get you to understand these are two different series, but both with the same number of terms. So our first result, well, let's think about what would happen if we added these together. So we're going to have the a's, and we're going to add to that b's. Well, we would certainly have a1 plus a2 and so on all the way up to an, and then we would have b1 plus b2 all the way up to bn. But because we're adding, well, we can group these in any way we like. So we could say, well, a1 plus b1 could be a little pair, and then a2 plus b2 could be a little pair, all the way through up to an plus bn could be a pair too, something like that. And of course, we could then rewrite this with our sigma notation. This is the sum from k is 1 to n of ak plus bk. And this result is really important. We can split up and we can put together different series that are adding. In summary, the thing to remember is the sum of a series plus the sum of another series, as long as they've got the same number of terms, can be brought together into one series. Just like that, okay? Put some brackets around that one. So that is a really important result. That's our first one. Let's carry on. What about constants? So our second result, let's think about this time. What would happen if we had some number at the front of every term? So let's call that number, that constant, c. So the sum of cak, where k is equal to 1, going up to n. Well, what would this look like? It would be c times a1 plus c times a2 plus c times a3, and so on, all the way up to c times an. But because they all have that c, we can factorize. We can pull out the c, and so we're going to have ca1 plus a2 plus a3, all the way up, look, to an. And of course, that thing in that bracket is just our original sequence. So we can certainly say that this is the sum between k is 1 and n of ak times that c. In summary, we have the following rule. The sum of cak is c times the sum of ak. Okay? Again, really important rule. Now, final result we're going to think about. What about if we have the sum of just a number, c? There's no a's in this at all, no b's, not much k's really. We'll write the notation. What on earth would this mean if there's no k involved? Well, every term is the same. Whether k is 1 or not, or 2 or 3, we're just going to have c every single time, c plus c plus c. In fact, all the way up to the last term, which is still c. Now, that isn't very interesting, but we do have one last piece of information we can use. We do actually know how many terms there are, because if we start at 1 and we end at n, there's going to be n terms in this list. So actually what we have here is we have c times n. So if we ever see this, the sum of a constant, well, it's just going to be the constant times the number of terms. This is a really important result too. So with those three results understood, let's take a look at some more examples where we can use and apply these. So let's start with this one. We'll read this carefully. Expand this series 2k and then write the expansion again underneath, but with the terms in the reverse order. Okay, let's just follow exactly what it says. So this will be, we'll call it Sn, 2 plus 4 plus 6. And I guess the second to last term would be 2 lots of n minus 1, with the last term being 2n. And it then says to do that again, writing the terms in reverse order underneath. Okay, well, that means we'll have the 2n first, and then the 2 lots of n minus 1. And I guess the second to last term this way around would be 4, and the last term would be 2. Okay, so what's that going to do? Well, let's read part B and find out. Add the terms vertically, and hence write an expression for the sum, Sn, of the first n even integers. So if we're going to be adding these vertically, what it means is, well, we are going to be adding these things up, right? There they are. All these things are going to be added together. So on the left-hand side, well, we have 2 lots of the sum of n terms. We're going to add them. And if we pair them up, we'll have 2 plus 2n plus 4 plus 2n minus 1 plus 2, n minus 1 plus 4 plus 2n plus 2. There we are. Okay, so what does that mean? Well, if we started to simplify these, I think we're all going to see the same thing. What we're going to have is 2 plus 2n plus 2 plus 2n plus, and of course, every single one is going to be the same thing. 2n plus 2, perhaps we could write there. 2n plus 2. They're the same, right? And how many of these have we got? Well, just like in the last kind of example, we've got n of these, right? We've got n terms. So if that's the case, well, we can use that same trick we used last time. 2 lots of that sum is going to be n times 2 plus 2n. So our job was to find what is the sum. Well, we'll just divide by 2, and we're kind of finished, right? The sum of those even integers is n times 2 plus 2n, all divided by 2. Can we simplify that? Yes, we could take a factor of 2 out of the top, maybe expand. We'll end up saying that the sum, and I'm just swapping this back in for Sn, of 2k, so those even numbers, will be n plus n squared. There's our answer. Now, final example now. Let's do something really tricky. I think this is as hard a question as we can be hoped to ask on something like this. So we've given some information to start with. You can see it there. The sum of k between 1 and n is n plus 1 over 2. And then that same sum for k squared, you've got a formula given. So the job is to write this thing, the sum of of k between 1 and n, of k plus 1, k plus 2 in its simplest form. Well, let's start by expanding the brackets. So if I have a sum, we'll have a k squared plus 3k plus 2. And we know already we can split these up. From those rules we found out earlier and derived earlier, we can split this up into its component pieces. We'll have a k squared. We can pull out the factor of 3, and we can write k as well. Plus, we can find the sum of all those 2's. And of course, we've got some things to swap out for this. We're given some values for k squared and k for that sum. So the k squared is going to be n plus 1, 2n plus 1 over 6, plus 3 lots of the k formula. Well, that's given as n plus 1 over 2. And then we've got all those 2's. And if we remember, we've got to do 2 times the number of 2's. Well, that's n. So we're going to have 2n also on the side. So now our job is just to simplify as much of this as we can and hopefully come up with a nice result. So we need to make the same denominator. So I think what we'll start by doing is writing everything with a 6 on the denominator, and we'll expand a few brackets as we go as well. So if we do that, the first term is pretty much the same. Let's keep the n outside and expand the double bracket, and we'll call that 2n squared plus 3n plus 1 all over 6. We'll times that second term top and bottom by 3 to get the 6 denominator. So that will be, we'll expand that bracket as well, 9n n plus 1. Now let's leave it like that. And then that last one will be 12n over 6. Now we'll expand those last things and collect up the terms. So what will we have? We'll have 2n cubed plus 3n squared plus n. That's the first one. Second one, 9n squared plus 9n. And we've got that 12n look on the end. And that is all collected into that one fraction now. We can collect up a few things. There's only one term of an n cubed in it. That can stay the same. If we collect up the n squared, we'll have 12n squared. And then we'll have 22n left over as well, all divided by 6. And I think now we can just divide through by 2. And then we'll have a pretty simple answer. N cubed plus 6n squared plus 11n all over 3. Okay, that is it. There's our answer. Okay, so that is a nice introduction to some of the notation and ideas surrounding sequences and series. If you've understood that, you're certainly ready to go on now and learn about arithmetic and geometric sequences and series.